The average, or mean, value of a periodic AC waveform tells us the steady state level that would give the same net area under the curve over one complete period. For any periodic function I of t with period t, the average is defined as I bar equals 1 over t times the integral from 0 to t of I of t dt. Think of the waveform as a road that goes up and down. If you fill the road with sand so that the total amount of sand equals the area under the curve, the average height of the sand layer is the average value of the wave. For a pure sinusoid, I of t equals I sub p times sine of omega t. The area over a full cycle cancels out because the positive half exactly balances the negative half, so the average is 0. For a waveform that is always positive, for example a rectified sine, the average will be a non-zero positive number. In practice, the average is useful for calculating DC power components, heating of resistors when the waveform is not symmetrical, and for designing filters that need to pass or block the average part of the signal. The RMS value is a way of converting a time varying a C quantity into an equivalent DC value that would produce the same heating effect in a resistor. V RMS equals the square root of open parenthesis 1 over t times the integral from 0 to t of v of t squared dt close parenthesis. For a sinusoid v of t equals v sub p sine omega t. V of t squared equals v sub p squared sine squared omega t. V of t squared equals v sub p squared divided by 2 times open parenthesis 1 minus cosine 2 omega t close parenthesis. 1 over t times the integral from 0 to t of v of t squared dt equals 1 divided by open parenthesis 2 pi over omega close parenthesis times the integral from 0 to 2 pi over omega of v sub p squared divided by 2 times open parenthesis 1 minus cosine 2 omega t close parenthesis dt. V sub p squared divided by 2 times 1 over t times the integral from 0 to t of dt equals v sub p squared divided by 2. V RMS equals the square root of v sub p squared divided by 2 equals v sub p divided by the square root of 2 approximately 0.707 v sub p. So the RMS of a sinusoid is the peak divided by the square root of 2. This number 0.707 appears in almost every AC power calculation because it tells you how much DC voltage would heat a resistor the same way as the AC sine wave. A real-world analogy: imagine you have a swing moving back and forth. The RMS value is like asking if the swing were held still at some constant height, what height would give the same average kinetic energy over a swing cycle. That constant height is the RMS value of the motion. Explanation: a full wave rectifier flips the negative half cycle of a sine wave so that the entire waveform is positive. Mathematically, the voltage after full wave rectification is V sub Fw of t equals absolute value of V sub p times sine omega t. Because the shape repeats every pi radians half a sine period, we can evaluate the RMS over the half cycle and it will be the same for the whole period. Derivation: V sub RMS equals square root of open bracket 1 over t times the integral from 0 to t of V sub Fw of t squared dt close bracket. Since V sub Fw of t squared equals V sub p squared times sine squared omega t, the absolute value disappears after squaring. The integral is identical to the sinusoid case. Hence V sub RMS equals V sub p divided by square root of 2. Average mean value of the full wave rectified sine is V bar equals 1 over t times the integral from 0 to t of absolute value of V sub p times sine omega t dt equals 2 V sub p over pi approximately 0.637 V sub p. Example problem: a transformer secondary delivers a sinusoidal voltage with a peak of 100 volts. It is fed to a bridge rectifier that produces a full wave rectified output. Find the RMS and average voltages across a resistive load. A solution: peak V sub p equals 100 volts. RMS: V sub RMS equals 100 divided by square root of 2 equals 70.7 volts. Average: V bar equals 2 times 100 divided by pi equals 63.66 volts. If the load is 10 ohms, The power dissipated is P equals V sub RMS squared over R equals 70.7 squared divided by 10 approximately 500 watts. The average voltage alone would give a wrong power if you used V bar squared over R. This illustrates why RMS, not average, is used for heating calculations. Peak, average, and RMS are three different ways to describe the size of a waveform. Peak V sub P is the maximum instantaneous value, positive or negative. It is like the tallest point of a mountain. Average V bar is the net area under the curve per period. For a symmetrical sinusoid, it is 0. For a rectified wave, it is a positive fraction of the peak. RMS V sub RMS is the heating equivalent value, the DC voltage that would deliver the same power to a resistor. Two useful ratios are form factor FF equals V sub RMS divided by V bar. It tells how peaky a waveform is relative to its average. For a full wave rectified sine, FF equals open parenthesis VP over square root of 2 close parenthesis divided by open parenthesis 2 VP over pi close parenthesis equals pi over open parenthesis 2 square root of 2 close parenthesis approximately 1.11. Crest factor CF equals VP divided by V sub RMS. It measures the ratio of the highest spike to the RMS level. For a sinusoid, CF equals square root of 2 approximately 1.414. For a square wave, CF equals 1 because its RMS equals its peak. Real-world analogy, think of a river. The peak is the highest water level during a flood, the average is the mean water height over a day, and the RMS is the water height that would carry the same amount of sediment, energy, as the actual varying flow. Engineers design pumps and filters using RMS because they care about the energy transferred, not just the average level. These ratios help us quickly compare different wave shapes without doing integrals each time. Explanation. Below is a table that lists the peak, V sub P, average, V bar, and RMS, V sub RMS, values for three common waveforms when the peak is taken as the reference. All results are derived from the standard formulas shown earlier. Sinusoid, V sub P reference, average voltage V bar is 0 over a full period. RMS voltage, V sub RMS, is V sub P divided by the square root of 2, approximately 0.707 V sub P. The form factor is undefined because of division by 0. The crest factor is the square root of 2, approximately 1.414. Full wave rectified sine, V sub P reference. Average voltage is 2 V sub P divided by pi, approximately 0.637 V sub P. RMS voltage is V sub P divided by the square root of 2, approximately 0.707 V sub P. Form factor is pi divided by 2 times the square root of 2, approximately 1.11. Crest factor is the square root of 2, approximately 1.414. Half-wave rectified sine, V sub P reference. Average voltage is V sub P divided by pi, approximately 0.318 V sub P. RMS voltage is V sub P divided by 2, which is 0.5 V sub P. Form factor is pi over 2, approximately 1.57. Crest factor is 2. Square plus or minus V sub P. V sub P. Average voltage is 0 because the positive and negative halves cancel. RMS voltage is V sub P because the value is constant. Crest factor is 1. Unipolar square from 0 to V sub P. V sub P. Average voltage is V sub P divided by 2. RMS voltage is V sub P divided by the square root of 2, approximately 0.707 V sub P. Form factor is the square root of 2, approximately 1.414. Crest factor is also the square root of 2, approximately 1.414. Triangular plus or minus V sub P. V sub P. Average voltage is 0. RMS voltage is V sub P divided by the square root of 3, approximately 0.577 V sub P. Crest factor is the square root of 3, approximately 1.732. Full wave rectified triangle, V sub P. Average voltage is V sub P divided by 2. RMS voltage is V sub P divided by the square root of 3, approximately 0.577 V sub P. Form factor is the square root of 3, approximately 1.732. Crest factor is also the square root of 3, approximately 1.732. The table makes it easy to look up the needed value for hand calculation exams. Notice how the RMS is always less than or equal to the peak. while the average can be 0 for symmetric waveforms or a fraction of the peak for rectified forms. A periodic voltage V of t is defined over one period t equals 4 milliseconds as follows. 0 milliseconds less than or equal to t less than 1 millisecond colon V of t equals 0 volts. 1 millisecond less than or equal to t less than 2 milliseconds colon V of t equals 10 sin pi left parenthesis t minus 1 right parenthesis volts a half sign that peaks at 10 volts at t equals 1.5 milliseconds. 2 milliseconds less than or equal to t less than 3 milliseconds colon V of t equals 5 volts constant. 3 milliseconds less than or equal to t less than 4 milliseconds colon V of t equals negative 5 volts constant. Find the average V bar and RMS V RMS values of this waveform. 1 point average colon integrate each segment and divide by t. Segment 1 contributes 0. 1 over t times integral from 1 to 2 of 10 sin pi left parenthesis t minus 1 right parenthesis dt equals 10 over 4 times open bracket negative cos pi left parenthesis t minus 1 right parenthesis over pi close bracket. Evaluated from 1 to 2 equals 10 over 4 times 2 over pi equals 5 over pi approximately 1.59 volts. Segment 3 contributes 5 times 1 divided by 4 equals 1.25 volts. Segment 4 contributes negative 5 times 1 divided by 4 equals negative 1.25 volts. Adding them, V bar equals 0 plus 1.59 plus 1.25 minus 1.25, approximately 1.59 volts. 2-point RMS colon square each segment integrate, then take square root. Segment 1, 0. Segment 2, 1 over t times integral from 1 to 2 of 100 sin squared pi left parenthesis t minus 1 right parenthesis dt equals 100 over 4 times 1 half equals 100 over 8 equals 12.5. Because the average of sin squared over a half cycle is 0.5. Segment 3, 1/4 times integral from 2 to 3 of 5 squared dt equals 25 over 4 equals 6.25. Segment 4 same as segment 3 because squaring removes sign another 6.25. Total mean square equals 12.5 plus 6.25 plus 6.25 equals 25. RMS equals square root of 25 equals 5 volts. Answer V bar approximately 1.59 volts. V RMS equals 5 volts. This problem shows how piecewise definitions are handled. Integrate each piece, separately keep track of signs for the average, but square for RMS so sign disappears. Waveform symmetry greatly simplifies the average calculation. Odd symmetry, also called anti-symmetry. V of t plus t over 2 equals negative V of t. The positive half of the period is the exact negative of the second half. The areas cancel, so the average over a full period is 0. Most pure sinusoids, V of t equals V sub p sin omega t, have odd symmetry, which is why their average is 0 without any integration. Even symmetry, V of t equals V of negative t. The waveform is mirrored about the vertical axis. For an even symmetric waveform that is also always positive, for example a full wave rectified sine, you can calculate the average by integrating over just half the period and then doubling the result. V bar equals 2 over t times the integral from 0 to t over 2 of V of t dt. Practical tip for exams: before doing any integral, check the symmetry. If the function is odd, average equals 0, skip the integration. If the function is even, integrate over half the period and multiply by 2. If the function is neither, you must treat each distinct region separately, as in the piecewise example above. Symmetry also helps with RMS calculations. Squaring an odd function makes it even, so the RMS integral can often be reduced to half-period integration regardless of original symmetry. For a half-wave rectified sine, only the positive half cycle passes through, the negative half is blocked, treated as 0. The waveform is V sub hw of t equals piecewise. Vp sin of omega t for 0 less than or equal to omega t less than or equal to pi. 0 for pi less than omega t less than 2 pi. Peak to RMS. The RMS over a full period is V RMS equals the square root of 1 over 2 pi times the integral from 0 to pi of Vp squared times sin squared of theta d theta equals Vp over 2. Peak to average. The average over a full period is V bar equals 1 over 2 pi times the integral from 0 to pi of Vp sin of theta d theta equals Vp over pi. Conversion example. Suppose a half-wave rectifier gives a measured average voltage of 20 volts. Find the peak and RMS. Peak Vp equals pi times V bar equals pi times 20 approximately 62.83 volts. RMS equals Vp divided by 2 approximately 31.42 volts. If the load is 5 ohms, the power dissipated is P equals V RMS squared divided by R approximately 31.42 squared divided by 5 approximately 197 watts. These simple formulas are often memorized for quick exam work, but they all come directly from the integral definitions shown above. Common misconceptions. Average and RMS are the same thing. Not true. Average is the net area can be 0. RMS is a measure of power equivalent magnitude. In power calculations, always use RMS. RMS means maximum. RMS is always less than or equal to the peak value. Only a pure DC constant waveform has RMS equal to peak. Form factor is the same as crest factor. Form factor equals RMS divided by average, while crest factor equals peak divided by RMS. They are different ratios. Zero average means zero power. A pure sinusoid has zero average voltage, yet it delivers real power. P equals V RMS times I. RMS power depends on RMS, not average. RMS can be found by simply dividing the peak by 2. That is only true for a half-wave rectified sine. For a full wave rectified sine, the divisor is square root of 2. For a square wave, it is 1. Frequently asked short answer questions. What is the RMS value of a 120-volt RMS sinusoidal supply? 120 volts by definition. The peak is 120 times square root of 2, approximately 170 volts. Why do we use RMS voltage when rating household appliances? Because RMS voltage tells the heating power effect, which determines how much energy the appliance actually uses. State the average value of a full wave rectified sine wave with peak V sub P V bar equals 2 V sub P divided by pi. How does symmetry affect the average of a sinusoid? A sinusoid is odd symmetric, so its average over a full period is 0. What is the crest factor of a square wave? 1, because peak equals RMS for a square wave. Understanding these points prevents loss of marks in exams, where the examiner expects the distinction between average and RMS to be clear.